Hello everyone, this is Hoang from the University of South Florida. So today I'm going to present our paper titled MOSE, Practical Multi-User Oblivious Storage by Secure Enclave. This is the joint work with Rouzbeh, Behnia, Yeongjin, Jang, and Attila and Yavuz. Let's first start with the introduction regarding to the data outsourcing. So data outsourcing provides an efficient storage infrastructure for one or multiple remote clients who would like to access the shared database on the cloud. So the clients can perform search, update, access, or even computation over the outsourced data being stored on the remote server. However, with many practical attacks being demonstrated recently, so access pattern leakage is one of the most security concerns in data outsourcing application. So in order to seal the access pattern, several Oblivious storage platforms have been proposed which harness the Oblivious RAM or ORAM in source in order to enable multiple users or clients accessing the shared database without leaking the access pattern of individuals. And the state-of-the-art Oblivious storage design harnesses a trusted proxy in order to execute the protocol, ORAM protocol for parallel access. So as you can see in this figure, there's a dedicated proxy. So this proxy has the ORAM controller. This proxy plays a role as the ORAM client, which will receive the request from multiple clients and execute the ORAM protocol on behalf of such clients with the untrusted storage server. So in this case, the access pattern will be hidden. However, the performance of all this state-of-the-art Oblivious design was limited due to the limited network bandwidth between the proxy and the storage server. For example, according to 1 gigabit network throughput between the proxy and the server, so it can only support up to 10 concurrent requests. And this significantly limit the application of the Oblivious storage to be used or to be deployed in practice. So the question is there any way that we can execute ORAM protocol in a more efficient manner? And the answer is in these days seems to be yes. So if we can harness a secure hardware to deploy the proxy directly on the untrusted storage server. And luckily, so the trusted execution environment or T-install has become widely available in commodity hardware in these days, such as Intel SGX. So Intel SGX has been available in almost the Intel CPU in these days. And let's move to our contribution in this paper. So in this paper, so we propose MOSE, a new multi-user Oblivious storage design which harnesses the Intel SGX. And we use and optimize the most suitable cryptographic primitives for secure hardware, specifically the recursive secret ORAM. So we use a recursive secret ORAM in order to execute the Oblivious access with the data stored on the untrusted storage, especially in the hard drive or in the untrusted memory. And we respect the secure hardware constraint when we design the MOSE. For example, in Intel SGX, there's a limited memory to be used inside the enclave. Specifically, we only have 95 megabytes. And we prevent the common side channel leakage while we deploy and implement the trusted ORAM logic inside the secure enclave. For example, we prevent the conditional branch leakage. And in MOSE, we support critical features for multi-user setting. For example, we support the access control against active adversary. So the active adversary can control a group of multiple users or even the storage server. And our MOSE is scalable to multi-user concurrent access. And we implement and evaluate MOSE with a large database. And in summary, so as you can see in this table, so we are about 37 times faster than state-of-the-art design, which use the dedicated proxy due to the limitation of the network between the proxy and the storage server. So effectively, so we can process around 374 requests per second, where in each request it only costs around 13 to 20 milliseconds for each access request. So compared to Taostar, this is one of the most state-of-the-art design, which only support 10 requests per second due to the limited bandwidth between the dedicated proxy and the storage server. And let's see the high-level design overview of MOSE. As you can see here, inside there's an enclave in the remote server. So this enclave will be used as a dedicated proxy that resides directly on the untrusted server. And everything inside the enclave it has assumed to be secure, so we can enforce and we can implement the ORAM controller inside the enclave. And this ORAM controller will query or perform an oblivious access to the data stored in the untrusted memory, including the access control data structure, in order to check whether the client has the permission to access a specific block or not. If yes, then such an ORAM controller will perform an oblivious access to the database. So in order to get that block for the client. And as you can see here, there's multiple user or clients that communicate with the enclave. And our MOSE can support hundreds of requests from multiple users. Let's go over the building blocks being used in MOSE. The first one is called a secure enclaves. So Intel SGX provides a concept called as enclave, which is a memory that are hardware-based isolated, encrypted, and integrity protected. So there's, as you can see in this figure, in the memory or RAM, there's a EPC, which stands for Enclave Page Cache. And in the EPC, there's an enclave, and all the secret data being stored inside the enclave are encrypted and integrity protected by the key. And this key is stored inside the Intel SGX CPU. And the EPC will prevent all of the unauthorized, untrusted component to access the data inside the enclave. So in order for the untrusted component to query the data inside the enclave, it has to be done through the econ, for example. And on the other hand, when the enclave wants to access some source of data or to call some kind of function that reside in the untrusted component, so it has to be done through the ocon operation. The second building block being used in MOSE is called a circuit ORAM, which is an ORAM protocol that follows the three ORAM paradigm with two main phases. So first of all, so the data will be organized in the form of binary tree, as you can see on the left figure. So for every single data block, so it will be assigned to a random path. And we have a component called a position map in order to keep track of the position or the path information of every single block in the tree. And there's another component called a stat that is stored in the client or in the trusted memory region that is used to temporarily store the block after being accessed. And to access a block, there are two main phases. The first one is called a read or retrieval. So this will read the entire path in the tree, but only keep one block into the stars. And once the block is read, it will be updated. And there's another protocol called as eviction that is used to push the block from the start back into the tree and try to push all the block from the upper level to deeper level as much as possible through a single scan. So for the more detail, I would suggest the reader to go over the secret ORAM paper to better understand the technique. And the eviction path is being selected to be deterministic and follow the reverse lexicographical order. Let's see the initialization phase in MOSE. Assume there's a data owner who owns the database DB, and there are k users who would like to access the specific items in DB. The MOSE will execute the Zen algorithm, with text as input db and k number of users, and output all necessary components to be used, including the EAC, which stands for Encrypted Data Access Control, and EDB, which stands for Encrypted Database. The EAC will store the permission information for every single user to the specific or to every single data item in DB. And the Jang algorithm will also generate an ORAM key, which is KO. After that, so all the necessary components will be uploaded to the storage server. And the EAC EDB will be stored in the untrusted memory region. And finally, the ORAM key will be sent to the secure enclave via the secure channel. The access workflow in MOSE was as follows. To access a specific data item in the database stored in the remote server, the user will provide the user ID, password, the block ID, and the operation, whether it's a read or write operation. And the user will encrypt all this information with the section key that were established between the user and the secure enclave, and send all this encrypted information to the secure enclave. The secure enclave will decrypt all this information and authenticate this user, whether this users can be authorized to perform an oblivious access or not based on his user ID and password. After that, the secure enclave will take the user ID and the block ID that he would like to access. He will compute the block ID that contain this permission information for the user ID on the specific BID, and execute the recursive circuit ORAM protocol on the encrypted access control position map in order to determine the path information of this specific block ID BID prime. Once it obtains the path information for this BID prime, it will execute the secret ORAM protocol with the encrypted access control in order to obtain this block. And then the secure enclave will decrypt this block, check find the permission or information of this user UID on the specific block BID. So if the user is not authorized to access this block, the secure enclave will compute the dummy block ID and access to the encrypted database position map through the recursive ORAM protocol in order to get the path information for this MID. Otherwise, if the permission, this user has the permission to access this block, the secure enclave will just provide with the correct BID and run the recursive ORAM protocol over the encrypted database and position map. And once it obtains the path information for the block that it would like to access, so it will run the secret ORAM protocol over the encrypted database in order to access or to obtain the block that it's read. So this block can be dummy if the user doesn't have the permission to access the BID, or this block can be just the BID if the user has the permission on it. And before sending back to the user, so the secure enclave will encrypt it with the section key and send it to the user, and user can use the section key and to decrypt it to obtain the block. And you can see here, so all the circuit ORAM protocol being executed here can be parallelized with the CPU by using the multi-core CPU and on the I/O access, as we will discuss in the next slide. So we do some sort of system optimization in order to achieve the highly scalable access in MOSE. The first one is the prioritization. So in MOSE, we prioritize all the computation and I/O access for each circuit ORAM access with multiple core CPU. We use parallelizable encryption such as AES counter mode. And another trick that we did in MOSE is we use matrix as an access control data structure. The advantage with the matrix is that it allows us to compute the user and the block ID permission check directly when we package it into the ORAM blocks. For example, you can see in this, so there's this user ID, UID, and BID. The permission of this can be stored in the ORAM with the block ID, BID prime that can be computed according to this equation. And the disadvantage with this approach is that the matrix is storage costly because the size of the matrix will be equal to the number of user multiplied by the number of data blocks. Let's move to the experiment. The first one is the configuration that we use for our experiment. The hardware we use is an Intel Core i7 with 32 gig of RAM and 4 terabyte of NVMe. We use a random database of size 768 gigabyte, and the block size is 24 kilobyte for the database entry and 12 kilobyte for access control entries. And we test on the network with 50 millisecond latency. For MOSE parameters, we selected circuit ORAM with the slash size of 80, the bucket size z equal to 2. We use deterministic eviction as discussed, and the recursive compression ratio is 256. And we select tau star as our counterpart for comparison. For tau star, we use the path ORAM with standard parameters. For specifically, the bucket size is 4 and the slash size is 80. And we test with the 1 gigabit of network with 10 millisecond latency between the proxy and storage server. And this is the experiment result. First, we run the micro brain mash in order to see how MOSE perform for processing one request. As you can see in the table, so with the largest database being tested, it only took around 28 milliseconds in order to process one access request. So that's why for MOSE, so we can offer around 53 operations per second for the database size 768 gigabyte. And the figure on the right is the cost breakdown, where we show the cost for every single component being accessed, including the I/O access to the encrypted access control or the database, and the computation overhead to access the access control on the database. And one thing to note that is this is the latency of MOSE without optimization, where we didn't apply any parallelization or some tricks that will be discussed later. And this is the optimized MOSE, where we take into account several optimization approaches, including the parallelization and caching. As you can see that we can cache the position map or the stash component directly on the memory without having to store it on the hard drive. So because the position map and the stash size is kind of small, so for example with 10 gigabyte of RAM, so we can cache 17 levels of the ORAM structure and the position map and also the stash, everything that we can store, we can cache directly on the RAM. And as you can see here, by using several system optimization, so MOSE can offer a throughput of 374 operations per second, where we take, for example, 6 CPU cores for the parallelized the cryptographic operation. And this is the comparison with tau star. So for the optimized MOSE, so the latency is around 13 to 20 milliseconds per request in comparison with 500 to 700 milliseconds in tau star. So as a result, MOSE was around 34 to 37 times faster than tau star. In conclusion, so in this paper, we designed MOSE, a practical multi-user oblivious storage with access control that offer the secure and efficient data processing on the cloud. And we demonstrate the practicality of using the secure enclave in order to enable oblivious data outsourcing applications. In this MOSE, So we mitigate the impact of network bandwidth bottleneck when we execute the ORAM protocol. We achieve the high scalability where we take into account several system optimization. And we offer the access control enforcement where we allow multiple users to access the shared database by having the access control data structure and use the ORAM in order to obliviously check the permission of every single user on the specific block. And due to the secure enclave, we offer the resiliency against active adversaries. And we provide the full security model and analysis in the paper if you want to check it out. Thank you. Finally, thank you for your attention and we are happy to address any of your questions.